over. First, our vocabulary is first word is term, which is a number and a sequence. So for example, 3, 5, 7, 9, all the numbers are terms. The initial value is the first term in a sequence, where 3 is the first term in the above sequence. Arithmetic sequence, a pattern that is repeated by adding or subtracting by a common term. The patterns can be increasing or decreasing. For example, 2, 5, 8, 11, 14. We're adding 3 to get to the next term. For 7, 3, -1, -5, we subtract 4 to get to the next term. Common difference. It's the term that you add or subtract to get the next term in an arithmetic pattern. The term can be positive for adding or negative for subtracting. So if we're using the above examples in the sequences, the common difference was 3, a positive 3. In the second example, the common difference is -4 because we're subtracting. Geometric sequence. It's a pattern that is repeated by multiplying or dividing by a common term. So for example, 1, 2, 4, 8, 16, we're multiplying by 2 to get to the next term. 64, 16, 4, 1, 1/4. So it's decreasing, so we're multiplying by 1/4 or we're dividing by 4. Common ratio or growth factor is the term that you multiply to get to the next term in a geometric sequence. So in the above examples, the common ratio would be 2 because we're multiplying by 2. In the second example, the common ratio is 1/4 because we're multiplying by 1/4. Let's look at objective 1. So this is about identifying the key features of arithmetic and geometric sequences. The pattern changes in arithmetic sequences. The pattern changes by adding or subtracting the same amount each time, which is what we went over in the vocabulary. So to continue the pattern, you are finding our vocabulary word for that was the common difference. And then you find this by subtracting a term from the one after it. The common difference is represented by the letter lowercase d. So let's look at a few examples. Write the common difference of each sequence. So we have 3, 5, 7, 9. So what I would do is I'm subtracting the term from the one after it. So 5 minus 3 is 2. It's a positive 2. So that means we are adding 2 each time. So our common difference is 2. The next one, let's see, 8 minus 2 is 6. So we're adding 6 each time. If we add 6 to 8, we get 14. And we add 6 to 14, we get 20. So our common difference is 6. Here we have 40 minus 50. That gives us a -10. So that means we are subtracting 10 each time. So it's a -10 for the common difference. Find if the sequence is arithmetic. If it is, then state the value of D, which is the common difference. If it's not arithmetic, then put an A. So number 1, we have 3, 8, 13, 18, 23, 28, and 33. So what we're going to do is we're going to subtract to find these. So 8 minus 3 is 5. And what I would do is see if I'm adding 5 to 8, do I get 13? And I do. If I add 5 to 13, I should get 18. And we keep going. And this checks out, so that means my common difference is 5. Number 2, negative 1/7 minus negative 0.7. Now, if we remember our rules of positives and negatives when adding and subtracting, a positive, this is technically times a positive, a negative times a negative, turns to a positive. So now this gives us an answer of negative 1. So if I were to subtract or add a negative 1 plus negative 1, I get negative 1/7. Plus negative 1, I get negative 2/7. Negative 3/7, negative 4/7, it checks out. So my common difference is negative 1. Number 3, if I were to subtract 2.2 minus 1.6, I get 0.6. So when I add 0.6, I should get the next term. And then when I get here, I see that 2.8 plus 0.6 does not give me 3.3. Okay, so this in turn is not arithmetic because the pattern does not continue. Okay, so that does not check out. Here, number 4, we have 53 minus 43. That is 10. So if I add 10 to each term, I should get the next one, which it checks out. So my common difference is 10. Now we're getting into geometric sequences. The pattern that changes by multiplying or dividing by the same amount each time, that is what we call a geometric sequence. I've underlined multiplying mainly because when we divide, if we're finding it by dividing, we can multiply by the fraction of that number, okay? So to continue the sequence, you need to find the common ratio. You find this by dividing the term by the one before it. So the growth factor is represented by a lowercase r. In here we have 48, 36, 27, 20.25. So we're dividing 36 by 48, and we get 0.75. So if I were to multiply each term by 0.75, I would get the next term. Okay, so my common ratio is 0.75. And you can definitely check that out on your calculator to see if it works. Okay, so let's look at a few examples. I'm going to do 10 divided by 2. I get 5. I'm just going to check the next one. 50 divided by 10 gives me 5. So if I were to multiply each term by 5, I would get the next term. So my common ratio is 5. The next one, 50 divided by 100 is 1/2. So if I multiply each term by 1/2, I would get my next term. And it does check out. Okay, so we'll pause here, and what you'll do is you'll click on this Google form and check for understanding. You'll answer a few questions and see how you do for Objective 1 before moving on to Objective 2. So find the common difference. I've underlined difference here because that gives us a clue that it's arithmetic. And I put an A here to symbolize arithmetic. So that means I'm going to be adding or subtracting, but here we're adding because the sequence is getting bigger each time. Okay, so as you can see, we are adding 2 to each term. So that means our common difference is 2. What would the next term be? So if we were to add 2 to 8, we would get 10. All right, let's practice some arithmetic sequences. Find the next term. We have 0 plus 0, 2, 4, and 6. So here we are adding 2 because, again, it's arithmetic. So if we were to add 2 to 6, we would get 8. Number 2. Okay, so my sequence here, 10, 4, negative 2, is getting smaller. So if I were to subtract 4 from 10, I would get a negative 6. So or 10 minus 4 minus 10 is negative 6. So I'm going to subtract 6 from negative 2, and that gives me a negative 8. Number 3. Okay, our sequence is getting larger by each term. So here I can see that if I add 3 to negative 3, I get 0. If I add 3 to 0, I get 3. So let's continue at the end. 9 plus 3 is going to give me 12. The next one, number 4, it is getting smaller. So let's see, 5 minus 8, or 8 minus 5 is going to give me negative 3. So if I continue this pattern of negative 3 each time, negative 4 minus 3 is giving me negative 7. Okay, and if you are uncertain about negative 4 minus 3, and you need to do a refresher of your adding and subtracting positives and negatives, let me know if you need the rules for that to go over. Geometric sequences. So geometric lets us know we're either multiplying or dividing. So here, number 1, my sequence is getting smaller. So that means I'm going to divide to find out what I'm going to actually multiply by. So 24 divided by 12 is going to give me 1, or 12 divided by 24, I'm sorry. 12 divided by 24 is going to give me 1/2. Okay. The other way you can do it is you can see 24 divided by 2 gives me 12. 12 divided by 2 gives me 6. but it's the same thing as multiplying by 1/2 over here. So 6 divided by 2 is going to give me 3. Number 2, our numbers are getting bigger, so I know 7 times what is going to give me 21? 7 times 3. 21 times 3 is 63. 63 times 3 is going to give me 189. Number 3. Okay, so my sequence is getting smaller, so I know I'm dividing. 189 divided by what will give me 63? That would be 3. So that means I'm multiplying by 1/3. When I continue this, 21 divided by 3 is going to give me 7. All right, number 4, the sequence is getting bigger. So I'm multiplying. 5 times what gives me 20? That would be 4. So now 80 times 4 is going to give me 320. Okay. All right. Here's some practice. Find the next term in the sequence. Number 1, what are the next 2 terms in the sequence of 5, 7, and 9? What you're going to do is you're going to go to your copy of this Google slide, and you're going to put your answers in here. Okay, you can use the text box to do that. All right, your next set of examples that you're going to try are right here. Determine if the sequence is arithmetic, geometric, or neither. So you're just going to write A, G, or N. Right? So you're going to find either the common difference or the common ratio. So you're going to find the common difference or the common ratio of the sequence. And once you find the first one, make sure it checks out for each sequence, for each term afterwards. Because if it doesn't, that means it is neither. Okay. Okay, so that is it for objective 2. You're going to, in your copy, click this Google form and check for understanding to see how you do before moving on to objective number 3. Okay, so you're given only the growth factor. Determine whether a sequence is growing or decaying. Okay, so if you look at the growth factor, is it growing or decaying? Determine whether a geometric sequence is growing or decaying. A question that we might want to ask about a geometric sequence is whether it is growing, which means increasing, or decaying, decreasing. Let's figure out how to do that. Let's start by examining a typical geometric sequence whose initial value, let's say 3, whose growth factor is 2. Okay, so again, remember, initial value means the first number in the sequence. So here, we have the first term is 3, which is our initial value. The second term is 6. Third term is 12. Fourth term is 24. You can see that the initial value in the sequence is 3. And you should also notice that at each step, we're multiplying the previous term by 2 to get to the next term. For example, we have 3 times 2 for the first term is equal to 6. So 6 is the second term over here. And now we have 6 times 2 is equal to 12. So 12 is the third term. Okay, and so on. So if we multiply 12 times 2, we would get 24. So it's pretty obvious that this sequence is growing because the numbers are getting bigger, right? So since the term started small and then got larger, you should also notice from your previous study of geometric sequences that this pattern of growth will continue. Based on this pattern, we also know that if we choose any earlier term, it will be smaller in value than any later term. So we can say that the first term is smaller than the second term term is smaller than the fifth term, the 10th term is smaller than the 17th term, and so on. We don't actually need to know what the terms are in order to say this. It's enough to know that the pattern of geometric growth will continue. Let's look at another type of geometric sequence. Let's give this one an initial value of 48 and a growth factor of 0.75 or 3/4. So again, our first term is 48. The next term is 36, 27, 81/4, or 20.25, and so on. So you can see that the initial value of the sequence is 48. And you notice that each step we're multiplying the previous term by 0.75 to get to the next term. So the second term is 36, and we did that by saying 48 times 0.75, and we got 36. 36 times 0.75, we get 27. So again, we're seeing that this geometric sequence is decreasing. Since the terms started at 48 and then they got smaller. Based on this pattern, we know that whenever we choose an earlier term, it will be larger in value than any later term. So the first term is larger than the second, the 11th term is larger than the 15th, and so on. Although the sequence is decaying or decreasing, we can still call its common ratio the growth factor. So it is still proper to say that this sequence has a growth factor of 0.75. Let's explore something else. Let's imagine the geometric sequence has an initial value of 7 and a growth factor of 1. Based on what we've learned about a geometric sequence, this means that each time we go to the next term, we multiply the most recent term by 1. So we have the first term is 7. 7 times 1 is 7, which gives us the second term. Second term times 1 also gives me 7, and so on. So what do you notice? We notice that each term is 7. Okay, so what makes this unusual is that we usually don't see a geometric sequence whose growth factor is 1, but it also serves to illustrate an important point. Notice that this sequence is neither growing nor decaying. You can see that its terms will always be equal to 7. This can lead us to a general rule about geometric sequences and their growth factors. It is this: if a geometric sequence has a growth factor that is greater than 1, then the sequence grows. Okay, so this is your greater than sign, greater than 1. So if it's greater than 1, the sequence is going to grow. It's going to get bigger each time. If a geometric sequence has a growth factor that is less than 1, then the sequence is decaying. It's getting smaller. So for our example where the growth factor was 0.75, the sequence was getting smaller each time. If it's a growth factor of 2 or 1.5 or anything bigger than 1, it's growing. If a geometric sequence has a growth factor that is equal to 1, the sequence is constant. It doesn't grow and it doesn't decay. Okay, here are some practice problems that you can work on. You're going to say if this is growing, if the geometric sequence is growing or decaying. You can use a text box to put your answers in. You can put a G or a D to signify that. The geometric sequence with an initial value of 6 and a growth factor of 1/3, is that growing or decaying? Initial value of 0.5 with a growth factor of 2. Remember, to figure out if these are growing or decaying, we are looking at the growth factor for each one. That will let us know if it's growing or decaying. The bottom two, you're saying which term is larger. So remember again, we don't need to know the sequence to figure that out. We just need to look at the growth factor to let us know whether the first term is larger than the second term. Okay, so work on those, and then you can do your check for understanding for objective 3 to see if you understand what's going on. And if you feel ready and you've done well on objective 1, 2, and 3, the check for understanding, then you can go on to Summit and take your focus area for patterns and sequences.